I remember that one.
It was
It was so tricky.
Interesting. All right, well, we're going to be talking about volumes, and Elliot is missing in action. He emailed me, so everybody say hi, Elliot.
Oh, Elliot.
Here we go. So, I want to consider a region R that is defined by the curve y equals x squared and the horizontal line y equals 4. Everybody sketch R. Go. Notice that your sketch needs to include intersection points. And your sketch should look something, your sketch should look something like this. Like that. Okay. Now I want to consider this interesting question. R is the base of a solid whose cross sections perpendicular to the x-axis are squares. What is the volume of this solid? Now, let's take a moment to visualize what this is talking about, because Danielle's giving me the funny look here. Did you do anything like this during your...
Yes.
Okay, you did? Okay. All right. All right. So, what we want to do is, first of all, understand what is being said. And what is being said is that R is a solid, and that solid is going to look something like this. If I sort of try to draw it, that's really bad.
It looks like a diaper.
Yes.
It's like a diaper, yeah. If I look at it, if this is the back of my solid and I do a back view, my solid in back view is going to look something like this. And if I look at it from the side, then my solid is going to look something like this. But it's really hard to visualize these solids, and I don't encourage you to try. Instead, what we need to do is really visualize just a top view, and we're looking at a top view right here, and a cross-sectional view. Now, to get at the cross-sectional view, here's what's being said. I'm going to consider just a cross-section that is perpendicular to the x-axis. And by a cross-section, what I mean is I'm going to take a mathematical knife and I'm going to slice through perpendicular to the x-axis, and I'm going to cut a small cross-section and bring it out and examine it. And when I take this small cross-section and bring it out and examine it, then this segment that I've shaded right here becomes the bottom portion of my cross-section. And when I examine that cross-section on its side, it is a square. Okay? So if we three-dimensionalize this, it looks like so, and like so. And this thickness right here is the thickness of that cross-section, just like that. Now our basic plan for finding these volumes is to construct a Riemann sum that estimates the volume and then we're going to take the limit as the width of our partition goes to 0 so that we get a definite integral. And then we are going to compute it. That's our plan. However, we can take this plan and abbreviate it just a little bit. Ultimately, what we're going to do is we're going to represent the cross-sections here as differential elements of volume. And we're going to construct the integral directly from those differential elements of volume, which is a shorthand for this entire process right here. So let's do this the long way once, and then we're going to come back in shorthands. In the long way, if I take and cover this entire solid with shapes that look like this, so on this point right here, I would use a relatively small square. Out here, I would use a larger square. My largest square is going to occur right here in the middle, and it's going to be a square that has a length and height of 4. So I cover that entire solid. What I'm doing is constructing an upper sum, a solid whose volume is guaranteed to be larger than the volume of the solid in question here. Then I can go back and I can do the same thing, but I can use squares that use the smallest width here. And when I do, I construct a similar looking solid, but its volume is going to be a lower sum. And so for each one of these, our squares have a thickness of delta x. And if I'm doing the upper sum, then we would say that for each x sub I, then I would choose the max to the min as appropriate here. And for the lower sum, you're going to have that. But for each one of these, we have a length of square that is equal to the top curve minus the bottom curve right here. 4 minus x squared. And so the one small piece of volume that we get from this guy right here is equal to the area times the thickness. And this is the key. Because I have chosen my cross-sections to be prisms, therefore, a prism is a constant cross-section multiplied through a height. Therefore, the volume of that little piece is equal to the area times the thickness. Yes? Yep. And therefore, the total volume is approximately equal to the sum of area times thickness for each of the pieces of. And now I take a limit. I let delta x go to 0. And when I do, then what I am doing is squeezing my volume between an upper sum and a lower sum so that the volume must be equal to the integral from first x to the last x plus of the area of my cross-section times the x. And we call this the cross-sections formula. Because you can see that although my shapes may be different, it's going to work out the same every time. No matter what cross-sectional shape I have, this process, as long as the cross-sectional shape is known, so that its area is known, this process of slicing up like so is going to give me a bunch of prisms that are upper and lower sum, give me the upper and lower sum estimates for the volume, and the little process is going to work with that. Now, because that process works the same every time, let's actually short-circuit it a little bit, or shorten it, by labeling our cross-section in this manner. We're going to cut for ourselves a representative element that I'm going to label with the label dx. And dx here is going to be a differential piece of x. And I'm now going to examine the cross-section, which is a square, and dx is going to be the bottom of that square, the thickness of that square. And the cross-sectional height is going to be exactly the same as the height right here, which is going to be top curve minus bottom curve. Okay. So that I can represent the area of my cross-sectional height as the area squared. And therefore, the volume is the integral from first x to last x, area, and that's it. How are we doing? Hopefully this is bringing back memories of last year. Good memories.
I think second semester last year was way more like smoother than the first semester.
Mm-hmm. Yeah, let's change up our problem just a little bit. R's base of a solid whose cross-sections perpendicular to the x-axis are now semicircles. Find the volume of R. Okay. So, again, we sketch the region R with its intersection points. Oh, excuse me, and then x squared. There we go. The 4 minus x squared was stuck in my mind from the previous problem. Thank you. There we go. Find the volume of R. So again, we draw our region R, and we draw for ourselves a cross-sectional, a representative cross-section. What changes about this is just one thing, the shape of the cross-section. So here's my cross-section, like so. Like that. And again, the shaded portion here is equal to the shaded portion here, so that we have a width dx. And again, the height of my cross-section becomes the dimension right here. Notice carefully that this dimension is the diameter and not the radius of those semicircles. Can't tell you the number of times that I and others have worked that fact out. So that the area of my cross-section as a function of x is 1/2 pi r squared, which is 1/2 pi times this distance, 4 minus x squared, divided by 2, plus 1b squared. So that my volume is now equal to the integral from -2 to 2 of area dx, which is the integral from -2 to 2 of 1/8 pi times 4 minus x squared squared. of the solid. Yeah, boy. I am just not with it today. R is a two-dimensional region in the plane. It doesn't have a volume. Yes. Yeah. Okay, now let's consider yet again one variation on this. R is the base of a solid whose cross sections perpendicular to the y-axis are squares. Find the volume of the solid. Now here is where our diagrams are really helpful to us. Again, I draw my base. With its intersection points. But now, when I take a cross-section, I am taking a cross-section perpendicular to the y-axis. And so here is the key to making sure that you don't dork this out. Pay attention to the axis. What he said.
Like, how did you get it? Like, make a card on top.
So we changed the equation.
Well, we are going to end up doing some substituting. That's exactly right. But the key is that we have exactly the same region, but now we're cutting perpendicular to the y-axis.
So we're gonna like, reflex the 90 degrees first.
Fortunately, we don't have to worry about that so much. All that we have to do instead is to recognize that now the width of my cross-section here becomes the width of my square right there. So that this width right here is this x-coordinate minus that x-coordinate. So here's the key. I'm going to need to solve for x as a function of y. Since y is equal to x squared, therefore x is equal to plus or minus square root of y. And the plus or minus reflects the fact that I have two different x values for a given y. One of them positive, one of them negative. And the whole length across right here is the square root of y minus the negative square root of y, or 2 square roots of y. So that the area of my cross-section is 2 roots y squared, or y. And the volume is therefore equal to the integral of... Good, that's right. I'm going to be integrating from the very first y to the very last y, which is from 0 to 4, and not from negative 2 to 2. I'm not going to go ahead and go through the computations, but when I do, the number that I get for this computation right here will be different than the number that I got for this computation right here. Because I have different solids, yeah. So that's cross sections. And it's relatively easy to set up. You remember last year we struggled with like, how do I visualize this?
Well, last year we had like solid and what's that?
That's where we're headed.
What's that called, like,
Solids of revolution. Yes, ma'am.
So, the other thing I got
Yes, this is the key. When I am finding distances along a straight line, I always do them by subtraction. So if I know the x-coordinate here and the x-coordinate here, I can simply subtract those two. Well, if I write these points right here in terms of y, so each one of these has the same y-coordinate, this point has an x-coordinate of root y, and this point has an x-coordinate of negative root y, and root y minus negative root y is 2 roots y. Another way that you can do it to check yourself is to observe that there is symmetry in this problem, symmetry about the y-axis, so that if this distance is root y, then the whole distance must be 2 root y. Okay. Now, let R be defined by y equals x squared and y equals 4. Find the volume of the solid generated when R is revolved about the line y equals 4. Now let's picture what's happening here. When we take the region R and we revolve it about the line y equals 4, we get for ourselves a solid of revolution. Yeah, a solid of revolution. And if we visualize, here's our axis of revolution, y equals 4. And when I take and revolve this region completely about the line y equals 4, I end up generating a shape that looks a whole lot like an M&M.
yes.
Yep. And this shape can be thought of by taking strips perpendicular to the axis of revolution. And that strip, when it goes around the axis of revolution, is going to generate a circular disk. In fact, really what I've done is to create a solid whose cross-sections perpendicular to the x-axis are circles. And in particular, what I could do, going back to our Riemann sum idea, is to take a bunch of disks on the outside, take a bunch of disks on the inside, and use those to estimate the volume and do the limit. But in practice, what I'm going to do is to take one of my disks and examine it like this. Here comes my disk, and it has a thickness of dx, like so, and it is going to have a radius of r, like so, and that radius is going to be the distance from the outer defining curve here, y equals x squared, to the axis of revolution. Keep that point in mind. R is the distance from the curve to the axis. It is not the distance from curve to curve. Now, accidentally, it happens to be the distance from curve to curve for this one problem. But in general, that's not the case. And so using our cross-sections idea, we can say that the area of our cross-section is going to be pi times the radius squared. So that the volume is going to be the integral from first x to last x of area dx, which is the integral from first x to last x of pi times. Now what is that radius? Let's identify the radius carefully as the distance from curve to axis. And that distance, Tife, again with the subtraction idea, is going to be 4, the axis, minus x squared, which is the curve. So that I get pi times the integral of 4 minus x squared dx. And that's our volume. Ring a whole bunch of bells from last year also?
Also, you
We also like take parts off.
the water.
Yeah, yep, we're gonna do that in just a moment here. Let's find the volume of the solid generated when R is revolved about the y-axis. Now this is an interesting problem which does not always occur. But notice in this particular case that R is going to actually coincide with itself once I flip it 180 degrees, right? And so in some sense I only have to do a half revolution to get the whole solid. But I'm going to end up with a sort of bowl shape or a bullet shape if you want to think of it like that. So sometimes if we have some symmetry, we can achieve a solid revolution by just doing a half revolution. But symmetry is required for that to work out. So again, we're going to take and divide up our solid into circular discs by cutting perpendicular to the axis of revolution. When we do, we get circular discs whose height is dy, and whose radius now is going to be curve minus axis. Again. So if I label this point right here as y for the y coordinate and root y for the x coordinate, then the radius as a function of y is simply root y minus axis, which is x equals 0. And the area of my cross section is then pi r squared, which is pi y. And the volume will then be the integral from first to last of area dy or pi r squared dy or pi times y. So by integrating vertically, I can now capture all of this in. How did I know I needed to integrate vertically? Because my axis of revolution was vertical. So to get cross sections that give me circles, I have to cut perpendicular to the axis of revolution. Let me summarize our discs method, and then we'll consider what happens if I have holes on the inside. First of all, for the general cross-sectional method, the volume is the integral of area dx or area dy. And the choice of dx or dy is dictated by the particular solid that is given to you. The problem will tell you cross-sections perpendicular to the x-axis. Cross-sections perpendicular to the y-axis. And then, in the special case of discs, if I have a horizontal axis of revolution, then I'm going to integrate with respect to x. Or if I have a vertical axis of revolution, I'm going to integrate with respect to y. In all cases, we are cutting perpendicular to the axis of revolution to get cross-sections that are disks, just like we did here, to get cross-sections. So you want to think of disks as a particular species of the cross-sectional method. Everybody good so far? Okay. Now, let's think about what happens if you have holes. Go, Jeff. Take it back. With cross sections, you're going to get language. Sections are perpendicular to the x-axis, sections are perpendicular to the y-axis. Yeah. Okay. So here, find the volume of the solid generated when R is revolved about the x-axis. Let's visualize what we're talking about. Here's my region R. Bless you. And now we're going to revolve this about the x-axis. Here comes our axis of revolution like so. And when we do, if I cut perpendicular to the x-axis, then what I get is a little strip of material that is now going to revolve about the x-axis, and it's going to create a solid whose outside is a smooth cylinder, like this. Whose outside is a smooth cylinder like this, but that has a funnel-shaped or a double funnel-shaped hole in the center. Everybody see the hole? Now the hole is created because there is an inside curve that is not identical to the axis, and because it is not identical to the axis, there's some daylight right there. So we have an outside curve that creates solid material as it goes around. We have an inside curve that is the end of our piece, our vertical strip right here. And because our vertical strip comes to an end before the axis, there will be a hole. So when I examine the cross-section that is formed, what I have then is a large circular piece with a circular hole in the middle. And we call this a washer. Not a washing machine, but a washer like you would use with a screw. And we can say that the area of this washer is equal to pi times the big radius squared. That gives me the area of this entire circular region, where the big radius is here. And then we can subtract away pi times the inner radius squared. So if I examine this on its, I do a top view of my washer, so that I have a big radius like so, and a little radius like so, then I'm picturing this as taking the entire area of the outer circle and subtracting away the area of the inner circle. So that my volume is now pi times the integral of big R squared minus little r squared. Please do not try to make that radius minus radius squared. It's not the same. And it gives you a completely different volume of a completely different solid.
Right. And that would be like the easy.
Yep. So now, all we have to do is identify what are the big radius and the little radius. But that's easy, because each one of these, big R and little r, are defined by particular curves. And the radius is necessarily always the distance from the curve to the axis of revolution. So that big R and little r both are curve minus axis, or axis minus curve, whichever one's common. So we identify here that the big R is equal to the outside defining curve, which is 4, minus the axis of revolution, which is 0. The fact that big R is constant simply means that the outside of this is going to look like a cell phone. And the inside radius is going to be equal to the inner defining curve, which is x squared, minus the axis of revolution, which again is 0. So that my volume is now equal to the integral first x to the last x of pi times big R squared minus little r squared dx. Big R squared minus little r squared. Yes, thank you. Wow, that was a failure on my part. Boy. Both radii are computed as curve minus axis. Now, Josh just pointed out a common failure that happens. Sometimes we're so happy to find our radius that we forget to square it. So I did that. I just illustrated that for you. Thank you. The second thing that I want to point out is not a problem so much as a possible benefit of symmetry. Notice that in this particular case, I'm integrating an even function. And so I can, if I want, and I frequently do want, to take the integral from 0 to 2 and double. Now what does that reflect? That reflects that my actual shape is symmetric, and that the volume of my shape from 0 to 2 is identical to the volume of my shape from -2 to 0, so I can just take half of it and multiply by 2. And what that does for me is it helps me not have to deal with so many negative values in here. So this is a frequent and highly recommended technique. Questions? No jokes today. The joke has been my poor execution on something.